B.6, the last video of part B, best case efficiency of quicksort. Yeah. So in this part, so let us do the best case analysis for the quicksort. Yeah. So let's look at under what situation we will have the best case. Yeah. It's pretty easy. Yeah. The most balanced partitioning will correspond to the best case. Yeah. The two files after each partition, they have almost the same size. We just studied that special case, we will get the best case efficiency. All right. So let's look at the diagram. Yeah. After one partition, we will get two subarrays with almost the same size. Yeah. When we use a recurrence relation, we can just assume two equal size n over 2. 2 times t of n over 2. Yeah. Two subproblems with the same problem size. Yeah. Then the comparisons, yeah, for this partition, yeah, the comparison when we scan all the elements in this array, you can see here we use big theta of n, and actually we can make it more direct. Yeah, because big theta, if you want to do the calculation, the big theta is not very convenient, right? So here we may like to use constant c times n to replace that big theta. Then it will be, much more convenient in our calculation. Yeah. All right. Yeah. In order to solve this recurrence relation, you can see if we work on it directly, it may not be that easy. Yeah. But here, I'd like to introduce a new method. It's called a recursion tree method. Yeah. When we construct a recursion tree corresponds to this recurrence relation, then it is very easy to get the estimate of the solution. Now, here, we will do the estimate. Yeah. It may not be very precise, but it should be a pretty good estimation. Yeah. All right, so let's look at the recursion tree. Yeah. Before we draw this recursion tree, we want to put our problem size n in two adjacent power of 2 numbers. Why we do that? It's easy because when we put this n in two adjacent power of 2 numbers, we can estimate the number of levels in the recursion tree. It's a binary tree. Yeah, binary tree, right? The reason binary tree, so look at the, 2 times t of n over 2. 2 branches. When we grow, every time we split t of n going down, we have 2 branches. So that's the reason we need to draw a binary tree, recursion tree. Yeah. All right. So then this tells us, because this typically gives us the problem size. You can see when the problem size finally in this fraction less than or equal to 1, we have to stop, right? We have to stop. Yeah. All right. So now we are ready to draw the recursion tree. But when we draw the recursion tree, we only write the non-recursion term. Here you can see the expression at each node that corresponds to the non-recursion term. That recursion part, when we draw the tree, we split into branches. We already use that structure. But at each node, we need to collect the non-recursion terms. So that's the reason we put the non-recursion terms at all the nodes. Yeah. All right. So then we do the split, going down in that way. Next, you can see at each level, the total cost for the non-recursion terms is the same, Cn, right? So this level 2 terms adding together, also Cn. This level 4 non-recursion terms adding together, also Cn, right? So you can see for all levels, if we accumulate all the non-recursion terms, we get the same number Cn. Next, how many levels? How many levels do we have in this recursion tree? You can see it is very close to k, right? Yeah, probably k plus 1. Yeah, k plus 1, very close to k. But the k plus 1, just plus 1, we can still use k for the estimate, right? The k we know in this range, very close to log base 2 of n. Log base 2 of n. Yeah, you can see, yeah. Now, it is very easy to see the total cost is big theta of n log n. Big theta of n log n. So you can see in this way, we can get a non-recursion, or we can get the estimate of that t of n, big theta of n log n. So that is for the best case of the quicksort. Yeah. All right. After that, next, for the average case efficiency, we cannot do the mathematical analysis here because it is extremely complicated. Yeah. I have never seen analysis for the average case efficiency for the quicksort because so complicated. Yeah. But we can use some way to get this big theta of n log n. Close to the best case, but slightly worse than the best case. Yeah, slightly worse than the best case. Yeah. Usually people do the experiments, write a program, do experiments many times, and get the data and compare average case efficiency and the best case efficiency. Yeah. And the ratio bounded by some constant. For that reason, so we can comfortably use this result, big theta of n log n, for the average case. Yeah. All right, so let me stop our last video B.6 right here, and we complete part B for the quicksort topic. All right.